so far. Many, it's because there are some talks which I didn't understand. So yeah, so that's it. Right. Okay, so yeah, this mic is a bit funny, but okay. So I'll switch between slides and the blackboard because especially I'll have to show some numerical plots. So yeah, they are very hard to draw on a blackboard. So yeah. So I'll basically concentrate on phase transitions, in some. Good. You think that's the maybe? Okay, so I'll concentrate on your conjecture was incorrect.
Do you have your phone next to it?
No, it's there.
There's some other mic is open. Is that mic open there? Is that mic on?
No.
All my connections are on.
Yeah, you're having an off day.
Yeah.
Okay. Anyway, yeah. Let me keep my phone far from me, even though I don't think that's the reason. But yeah. Oh. So in this talk, I'll basically concentrate on.
It just doesn't like that side of the
Yeah,
board.
it's basically that speaker on top.
Hmm.
That's why you could get.
But I have to. So I'll basically talk about some thermal phase transitions. Oh yeah, that's correct.
But then you have to use that side of the board.
But there's a horizon there, so
It's all right. I mean,
It's okay.
Yeah, let's sort of
Ignore that. Yeah.
careful on that side of the thing.
Yeah. How did Connor manage to do that? But anyway.
Yeah.
Okay.
No.
Anyway, okay.
Yeah.
So I'll concentrate on some 2D classical models and then thermal transitions.
Doesn't like.
Actually, I can take this off and shout, but I don't know whether that affects the
Let's go stay there for too long.
Yeah.
Yeah, I will just avoid that region. Yeah. And also I'll talk about some 1D spin chains, which are quantum and quantum phase transitions. Okay. So I don't think the emergence of CFTs in lattice critical models was covered in Connor's preparatory lecture. Perhaps not. So I'll spend some time in just revising some things quickly, and because I think it's important, and then I'll go on to explaining some of the things here in my talk. Okay. So of course, if you have a theory on a lattice, and I'll basically concentrate on spin half models on a lattice or Ising models when I go to the classical context, because as I already saw, that's sort of familiar to many of you as well. And anyway, it's an interesting and simple playground to start with. So the point is that these models, even if you tune the coupling to be at the critical point of the lattice model, are clearly not conformal field theories. Okay, that's because the theory is on a lattice. It doesn't have full rotational symmetry. It doesn't have full translation symmetry. So cannot be a CFT. So there is some sense in which we need to understand it. So, well, one sense is if you keep renormalizing the theory and go to longer and longer length scales, then you ultimately flow to some RG fixed point, and the field theory at that RG fixed point is a CFT. That's one way of thinking about it. Okay? But let me say some statements to that effect, which will make it a bit more precise, and even this idea of state operator correspondence for lattice critical points. So all I'm trying to motivate is, suppose we have some spin half system here and L sides, then of course the Hilbert space is 2 raised to the power. But not all the states here are described by a CFT. Only a subset of the states here are described by a CFT, and there you can use this. Okay. So let me first come to this notion of symmetry enlargement. It's well known that when you go to critical points in theories, you can often have symmetry enlargements, right? For example, you often have full rotational symmetry, full translation symmetry. You of course have scale invariance, and of course, if you are in 2D, many a times that leads to a full conformal symmetry, okay, for certain kinds of theories. Okay. So, because I said certain kinds of theories, I'll only consider cases where the Hamiltonian or the interactions are sufficiently short range. Then you can promote some of these global symmetries like scale invariance and rotation and stuff to local things, and then CFTs emerge. Good. So let me first just very quickly discuss the symmetry enlargement business. And to just motivate that, let me take the 2D Ising model, the classical 2D Ising model, where you can exactly solve it, right? So you can write the full solution on the lattice thanks to Onsara. Okay? So let's do that. And then let's see in what limit something which resembles a CFT appears. Okay? Because again, you should keep in mind that the full theory is not a CFT.
So when you say that L size is the Hilbert space that you mentioned,
Yeah,
and a subset of this is the CFT. So can you please elaborate?
of course I'll elaborate. As I go on, yeah, I'll elaborate. And then I'll go to these results, but it's okay if I don't finish showing all the results, that's fine. So now here it is. Okay, so that's an engineering flaw we discovered today in an engineering institute. So the 2D Ising model is well known. So let's just draw square lattice, and let's say there are spins on each side. So let me just denote them by sigma I comma j. So I and j runs on integers, right? And the Hamiltonian is simply nearest neighbors, sigma ij, sigma k, whatever. So it's bad notation, but okay, you understand what I'm trying to say. Okay, then all you do is raise your temperature, and at a critical temperature, you hit the critical point. Okay. So now at the critical point, if you just look at the Onsager solution, yeah, which is also given in Kersenbaum's textbook. Yeah, I'll draw event horizon here. Yeah. Then the solution is complicated, but in some cases you can sort of write it simply. So for example, if I just look at a row and calculate the spin-spin correlation at some temperature, well, actually the temperature is at the critical temperature here. So this n is positive integers. Then for this, the solution has a slightly easier form. These are gamma functions. Okay, good. But now, this is not very useful if you just stare at it, unless you're in love with gamma functions. So it's not very useful. What you should do then is do a large R expansion of this thing. So when I say large R, there is a lattice length scale here. Let's say that's 1 in my units because I'm just considering integers. And you just consider an R which is much larger than 1. Okay, and then you do an asymptotic expansion of this thing. And that's not such an easy thing because the full solution is reasonably complicated. And if you want details, you can look at this guy. I'm really trying to provide that. Look at this. So at large R, the solution looks like this. Now I remove this restriction that I'm just going on a row. I just have this restriction because I just wanted to show you how the form looks, but it's more complicated in general. But in any case, I'm doing a large R expansion now. There's some constant which one can work out. And then there are some interesting things. And CFT experts will soon recognize these things once I tell them what these are. So this is an exact result, right? So, sorry. Oh, right. Okay, good. So let's stare at this. So this R is just measured in the usual way. You just take the distance from 0, 0 to m, n. And okay, so this is the familiar result from CFT. If you have an Ising CFT and you take, and it has only two primary operators, well, it has three operators, three primary operators. One is identity, but then it has a odd in Z2 operator, let's call that sigma, and even in Z2 operator, let's call that epsilon, right? So the scaling dimension of the odd in Z2 operator gives you 1/4, right? So this is that part, right? So at very large length scales, you see something like a CFT merge. But you see, there are all these interesting terms which are subdominant. And let's look at the structure of these things. This guy is 4 theta, this guy is 8 theta, and so on. So why does this happen? This happens because the microscopic theory is kept on a lattice, and the lattice is 4-fold symmetry. So only sinusoidal functions with 4 theta, 8 theta, 12 theta, and so on will emerge, right?
Sorry, what was that?
Oh, theta is the angle. So there's some 0, 0, there's some n, n. So theta is this. Theta is this. Okay? So you see, this is the remnant of the lattice effect. Okay? So of course, full rotational symmetry only emerges asymptotic. Right? Because then you can sort of ignore these terms if you wish, and then this is a rotationally invariant. That's point number one. Okay, so I hope you see why I'm calling this symmetry enhancement. Okay? Now it's even more important to stare at these and think about what these guys are. And this will become important later on.
This should depend on lattice size.
Which one?
Like this result.
No, but I already told you that the lattice size is 1. Yeah.
All lengths are in. So,
Yeah, all lengths are in unit of 1. So I'm doing an expansion like this. I'm doing an asymptotic expansion like this. Now let's stare at these corrections and how they come about. So you see, I'm looking at some lattice operator here, local lattice operator. Now you see, in CFTs, we know that there are primaries and there are descendants, right? However, you are on a lattice now, and if you express a lattice operator in terms of your field theoretic operators, which are your primaries and descendants, then there's an infinite series you get on the right hand side. Okay, and these are just reflections of that. So let me just write it in a form which will make it immediately clear what this is. So basically, these terms are nothing but coming from the stress energy tensor. So I'll just write something and then it'll become apparent to you. So on a lattice, there's a spin 0 term, there's a scalar. This is a spin 4 term. Okay? So basically, this guy, so let's just look at the leading subleading part. Okay, so this guy is coming from PT bar, and that's spin 0. So these are the descendants, right? And this guy is coming from T square plus T bar square. and that's spin 4. Okay, and so on. And these are of course subdominant compared to the primary.
When you say TT bar, you say TT bar times sigma, or it's the same.
Yeah, and exactly, time sigma, because there's an overall thing. So, yeah, so roughly speaking, and I'll come to it more, you have sigma, that's like some C times the sigma of the CFT, where C is some non-zero number, which is non-universal, plus all descendants which are Z2 odd. Z2 odd just comes from symmetry here because this is it. And that's it. There's no other restriction.
It confused by the power law because it's 1 over r squared and TT bar has weight 4. So why is that? Shouldn't this be some level 2 descendants?
No, I think the power law works out
Shouldn't
really.
it just be a TT bar and the T plus T bar? Because it's 1 over r squared, right? So
Yeah.
and TT bar is power 4. So see what I'm saying?
Mm-hmm.
If it's a level 2 descendant.
Okay, this maybe we can sort out later, right? Yeah. But yeah. I think the higher powers come as R square, R4, and so on. Yeah. Okay, yeah. Okay, so this is one thing. So I hope this point is clear why I'm calling this symmetry enlargement. So that's point one. Yeah.
That's true.
Yeah.
So I should include the additional terms as some kind of, lattice deformation of my CFT. Is that?
No. See, the point is you're calculating the correlator of a local operator on a lattice. Right? And maybe when I say something more about the state operator correspondence, it'll become clearer. But even when you're using state operator correspondence, you have a lattice problem. You're ultimately calculating correlation functions of local operators on the lattice. They have a complicated expansion in terms of your field theory operator. That's not so non-intuitive, right? The field theory operators are obtained after a lot of coarse grading. So when you express the lattice operator in terms of these guys, there are lots of terms. That's it.
Yeah, we are just not measuring two primary.
Exactly. We are not measuring two primary operators. We are on a lattice, so we are just measuring things which are local on the lattice. That's it. Yeah.
So I'm a little lost actually. So you started off with something which was a sigma, and
And this is on the lattice, right? This is just from the Onsargan function.
where is your R on the right side of that?
Oh, as I said, sorry. I started here, and as I said in this small picture, this is 0, 0, this is n, n. So the lattice unit is 1. Then we just measure distances in the U shape. So R is that distance. This distance.
Okay,
This is very large.
fine.
Yeah.
Fine. But in your
Expansion.
No, the capital formula there. The S. How is S? I mean, what's
Which formula? Sorry.
your the formula in between the exact formula.
Values based on just the row, the first one.
Yeah. Yes. What's the where are these two operations?
No. So see, this is the thing. Yeah. So here these are on the row. So this is 0, 0.
Okay.
And this is, let's say, 0, n.
All right.
Right?
Okay.
And the n appears here. This is a product of gamma function. It's a very complicated formula.
Fine. Okay.
If you take this formula on Mathematica and you massage it, then you will see that in the large R limit scale invariance emerges.
All right. That's
Which is what I've done here.
Okay.
Which is what these people have.
And once you expand this out.
In the large R limit.
Yes, in the large R limit, what you are saying that this first term is this CFT like.
Exactly. Just the primary contributions. The next terms are descendant contributions.
Yes, but what sort of descendants, right? Why should I expect an R square out there? Is there any reason?
Yeah, there's some reason, but I'm just fogging out on the power counting here. And I'll come back to you and to Anthony also. Right.
Actually, we'll just again to understand one. Sorry.
Yeah, sure.
So, yeah, I mean, let's say we didn't take 8 we want, kept the
What is the
lattice space. Okay.
No, but
So
that
does
is
it-
just some trivial rescaling of the
Yeah,
thing.
it's a trivial necessary, but if I take that A and scale it to 0, like say
No, I don't scale A's to zeros. But you can do it, but you understand. I mean, it's just
Because it's continuum.
No, but there are many ways of taking continuum. There are always two length scales involved because you have to have some dimensionless objects. Now it's your choice if you want to keep the smaller length scale fixed and the bigger length scale to infinity, or you want to keep the bigger length scale fixed and keep the smaller length scale pushing to 0. That's just semantics. Right.
Yeah, so just going back on that, the sigma should give you, sir, I mean, you should be in the module of the sigma, right? So in that case, it's the descendants of the sigma.
Correct.
Where did I mean, these from?
Well, I looked at this answer and this looked like T to me because it cannot be anything else. Yeah, T times sigma. Exactly. Yeah, it's T times sigma. That's correct.
Okay.
Yeah.
So
Because there's a sigma outside. Yeah. It's T times sigma. Correct.
So sorry,
That's L minus 2.
yeah, okay.
Yeah, it's L minus 2 and L plus 2. Yeah. They are those guys. Yeah. Okay, can I go on?
Yeah.
I think I'll continue my world record of not finishing a talk. Yeah. Okay, good. So far, everybody's happy or unhappy? Very good. So it's clear that symmetry enlarges here. Now let's come to the second point, this operator state correspondence. Now this operator state correspondence can be understood both in the classical setting, but you need to think of transfer matrices. So maybe that's whatever. So, but in terms of the 1D quantum problem, it's much more obvious because you just think of the spectrum of your Hamiltonian. So let me just go there. Okay. So as I said already, suppose you have a spin chain and there are 2 raised to the power n states. Not all of them are described as here.
Although you can also use the.
Oh, sorry. Yeah, I forgot. Yeah, late.
Points.
Yeah, sorry. So suppose you have a lattice model. Suppose you have a lattice model and you sort of tune it to the critical point. Just to give you an example. So the 2D Ising model, if you consider its one lower dimensional quantum analog, that's the famous transverse field Ising model, right? And the transverse field Ising model is a fully solvable integrable theory. So basically, now these are quantum spin halves. And the theory looks like this. So these are Pauli matrices at each side. This sigma z, this sigma x. And of course, this term does not commute with this term, right? So there's quantum fluctuations here. And as you tune h, you can have a phase transition. So in this theory, you can actually show that the phase transition is at h equal to plus minus 1. Okay? So if you draw sort of a phase diagram, where this is h, this is plus 1, this is minus 1. This guy is like a ferromagnet. This guy is like a paramagnet. If you just look at the ground state for a very large spin chain. And here, the Z2 symmetry of the problem is spontaneously broken, whereas here it's unbroken. And these are the critical points. Okay? So just to keep an example in mind. Of course, for some more complicated problem, you might need to do some additional numerics or something to figure out what's the critical coupling. Here you can derive the critical coupling A either using duality, because in the Ising model there's a duality which takes h to 1 by h, or you can just solve the theory, because here it's solved. Good. So now, I said that there are 2 raised to the power n states here. Now let's sort of draw an artist's impression of those states as the coupling is changed. Okay. And let me just concentrate on positive h, because there's a unitary transformation which takes h to minus h here. So if I just understand the physics here, I understand the physics there. Okay. Good. So here what I'm going to say is general. So there are lots of energy levels. So energy is increasing like this in a big system, right? So maybe this is the ground state, energy is 0. Then of course there are lots of levels. There are 2 raised to the power L levels or something, right? But something very interesting happens. So this is by the way a finite system, okay? So there are finite gaps all around, but I'll try to draw this as properly as I can. So basically, if you go to Hc equal to 1, what happens is that there's a huge accumulation of states near the ground state. This is a generic property of all critical points. Sorry, all continuous critical points, not first order. This is true in high dimension also. So I tried to draw an artist's impression, but really what's happening is as you really are at the critical point and your system size is really big, there's a huge accumulation of low energy states near the ground state. And of course, if you go really high in the spectrum, if you just follow this, you won't even know that there's a phase transition, which sounds reasonable, right? Good.
So CZ is exactly solvable. We actually know what fraction of states
Yeah, here if you work really hard, you should be able to do everything. Yeah, in this particular model.
Yeah.
But this is a very generic state. Yeah. So in particular, there are states. So let's just focus on H equal to 1. In particular, there are states whose gap to the ground state is closing as 1 by L, where L is your system size. Okay? So now I'm restricted to 1D again. Okay? I claim that these states are described by the operator state correspondence, not any other states. Okay, so is the statement clear now? Good. So what is the correspondence?
So just to again ask something. So in the middle of L goes to infinity.
This will become totally gapless.
Yeah, but are you saying that the ground state becomes infinitely degenerate?
See, I don't like to push this to L tending to infinity because in a CFT, you know that it's a completely gapless theory, so it's good to have a regulator. But strictly speaking, if you take L tending to infinity, there'll be gap closings of all sorts. Yeah, many states will just hit on the ground state. But see, this is the limiting sequence. For any finite L, the ground state is non-degenerate. For any finite L.
True.
And so you see, there's the sequence of gap closings.
Yes. But in the string, limit.
I am very. I don't like that limit.
Okay.
I don't like that.
Sorry, one more time. So there is a huge accumulation.
Yes.
And not all members of that accumulated states go as 1 over L. The gap goes as 1 over L. Or for everyone, the gap goes as 1 over L.
And that's a good point. Yeah. So if you're strictly in the extremely large L limit,
Everyone.
the guys which are accumulating here, they'll go as 1 by L.
All of
Yeah, exactly. In an extremely large L limit. Of course, if L is 10 million, there are always finite size corrections, but you see what I'm trying to say, right? So
in that sense, it might term it as degenerate infinity, but
Yeah, but
saying it doesn't want to go to that.
Sure.
yeah, because
I mean, sorry. No, before. So
Yeah.
if I go into the Fermi picture, you have this band, and the bottom of the band hits the ground state, right? That's the
no. So which statement are you contesting?
I'm just asking why is it infinitely big in the third degree?
I don't like to think of L tending to infinity.
Okay.
See, okay, if you want to think of L tending to infinity, what will happen is there will be some complicated dressing here, and it'll give you whatever the ground state is in the infinite L limit,
Yeah.
and it'll actually be strictly gapless above that.
band, right?
So the band is a gapless object. It's not a gapped object.
Continuum. So not
Yeah.
all states in that band is going to be in the ground state. It's
Of
only
course
the
not.
bottom
Of course not. Of course not. But it's nonetheless gapless.
Yes.
Yeah,
But it's not infinitely given.
No. I'm not saying it's infinitely degenerate, but the excitation spectrum is gapless.
Yeah, no, that is fine. I was just saying that do all of the states keep the.
No, but see, there's a quantum problem.
It's not a fragment.
No, it's not a flat band because it's a quantum problem, right? So what is going to happen is because of degenerate perturbation theory, they'll be mixing and stuff, and you'll pick up some linear superposition, right? Okay, yeah. But I personally don't like to directly figure L tending to infinity. Yeah. And I think CFT people also sometimes don't like that. Anyway.
I'm sorry to say that, but this is same as keeping L fixed and taking.
No, okay, yeah, you can do that. That's yeah, but yeah, that's the same as taking A equal to 1 and keeping L to it. Yeah, it's the same thing. Yeah. Both approaches are the same because at the end of the day, there's a dimensionless number in your problem which is related to L by A, and so you can do whatever you want. You see what I'm saying, right? So as long as the dimensionless number is fixed, you do whatever you want. Okay, good. This is taking more time than I expected, but that's okay. Yeah.
This is a stupid question, but since you said that you are going to consider only those states which are closing as IO,
There you can make a state operator correspondence to a emergent CFT.
right? But is there any reason then why you should take exactly one, right?
Yeah, there is a reason for that, but I don't have time to show that here. Roughly speaking, the reason is this. Suppose you write the partition function of this theory, and you write the partition function of this theory on a big torus. If it's a CFB, then the partition function should only depend on, of course, some rescale temperature, but other than that, just the aspect ratio of the torus, right? Because there's nothing else in a CFB, right? And of course, some universal data, which are some order one numbers. But then you can show that if you take these states, then this property is satisfied. If you start taking these states, then this property gets lost. There are some non-singular corrections which breaks that problem. So I hope that answers your question.
Just continuing what you said. Let's suppose you compute this partition 24 for this space. Do we have model invariance?
I don't know what is model invariance, so you should ask somebody else. But you have a CFT. So whatever the CFT has, it should have this.
Of course.
Oh yeah, so it is consistent on it.
So effective theory will have that in the sense that I think safety does, but not the entire theory.
No, but the entire thing is not a CFT.
Yeah, it's not a safety. So
But this theory is a CFT. This theory is a CFT. So you'll have all these
I
properties.
can set the partition of the nine. Yeah, just using those states probably is.
Yes, yeah, it should. Yeah. Okay, good. So let's go on. So suppose you just look at these guys as E0, E1, E2, and so on. So of course they're changing as a function of H. Maybe I'm going into too much details, but maybe that's okay. Anyway. So suppose you look at this E alpha for a lattice problem at the critical point. Now I'm talking about the state operator correspondence. Then basically in the large L limit, you will get an equation like this. Our good old friend, the central charge, makes an appearance here. Oh, and I should have defined something. So when I'm writing this equation, I'm always imagining a spin chain with periodic boundary conditions. Always be that. So there's a spin chain with, let's say, L sides or whatever with periodic boundary condition. The reason I'm doing that is because, as you know, Cardi very powerfully uses these things where you go from an infinite plane to a cylinder using a conformal map, and basically, if you do all that faithfully, you'll get all these things.
Yeah, and that's the trick.
Exactly. Yeah, that's the trick. One sec. Let me just write one more equation and then you can ask. And this guy is quantized because this is nothing but a lattice movement. So this guy is quantized. Oh, go on.
I'm guessing probably in A times L.
No, I'll come to that. Yeah, because I've just written A, but of course you're right, A is an extensive object, of course, but I haven't told you what A is, right? So, yeah. So, A and B are non-universal. They depend on some details, but this thing is universal. This X is also non-universal. sorry, I'm really bad at notations. This should be L. But this X is greater than 1. So this is subdominant compared to this thing. So if you go to really large L, then you can forget about this. Okay. So what is this A? This A is nothing but, so you go to the thermodynamic limit, epsilon naught is the energy per site at the critical coupling. So this A is epsilon naught times L. What is this B? This B is another emergent thing. This B is just nothing but the velocity of excitations. So this is a lattice problem, right? So as we have as you might fondly remember from your solid state course, whenever you have a lattice, you have something called a Brillouin zone, and you cannot have sines and cosines there like in simple ways. So, I mean, you cannot have like linear and quadratic spectrum there in simple ways because, of course, you have to have periodic functions. So, roughly speaking, things might look like this on a lattice. But if you go to really low energies, then your spectrum starts looking like this. Right? And this is the excitation velocity of the linearly dispersing. So this is also a non-universal content of the theory. But if you fix them, then everything is fixed. And here there is nothing to fix. This is just the momentum of each of these eigenstates, and that momentum is quantized from the lattice because you're just putting it on a ring. Okay, so there's nothing to fix here. These guys are integers. Okay, good. So what is the connection to a CFT here?
Sorry to interrupt you, but there's something here I never understood, which is why isn't there a constant
Where?
the large elements?
Where?
For the relation between the energies, there's some extensive part that goes without. There's the 1 over L part that gives you the CFT dimensions.
That's a good point. So, right. It's related to the fact that, as I said, see, I'm measuring gaps here, right? Oh, but yeah, you're right. If I have a constant term in the gaps, it'll still vanish. So short answer is, that's a good point. Yeah, I cannot rationalize it from whatever I've told you till now.
How the gap vanish and the difference?
No. He's not saying that. He's saying that let's put an order 1 term here.
Yeah, there's I mean, 1 by L, where did the.
I mean, yeah, so he's asking why is there no order 1 term here? That's his question. Well, firstly, that order 1 term would still just be something which contributes here, not here, because here everything should push down as 1 by L. But
The field experiments on the lattice, this order 1 term is really 0. Right?
yeah, it's really zero. Yeah, exactly. Yeah, I'll think about it and yeah. Because from whatever I've said, it's not obvious. Maybe if I go back to that partition function answer I told you, maybe the answer is there. If I add an order 1 term there, I think what would happen is in the long torus limit, maybe it's not just a function of the aspect ratio, but I need to just recheck that. Maybe. Yeah. Okay, good. Now I'll write something there. I won't erase this. This is important. So now let's write what these guys are. And then you'll see that really these are like CFT-like statements. This is the spin, rather this is the conformal spin. This index P is nothing but an index for a primary operator. An Ising CFT just has 3 primary operators. Some more complicated CFTs may have more primary operators. These non-zero integers are for the descendant operators, and these are integers. Okay, but they describe the action of descendant operators. And similarly, this is the conformal spin. So you see, if you follow Cardy's works and other people's works carefully, this is the consequence. Okay, so now you see this is the state operator correspondence. I'm of course not going into details, but yeah. I mean, for example, for an Ising thing, all I'm trying to say is, let's say you have an Ising CFT, just as a backup example. You know, roughly speaking, these guys are some complicated towers of states, right? And in the CFT language, you see the same tower of states. When you act by the primary or I mean, of course, there are three primaries here, or its descendants, and this is the correspondence. Okay, good. So far, so good. Now the last point. Okay. So now, of course, as we heard, in CFT, there's a universal data. The universal data is specifying the central charge C, the scaling dimensions of the primary fields, and the OP coefficients, right? So you might ask, how do I figure this out from the lattice? Well, from the lattice problem, if you look at the scaling of the ground state energy as a function of 1 by L, you can figure out the central charge. Because for the ground state, delta naught is 0, right? So if you just put that in this equation and you look at how the ground state varies as a function of 1 by L, and you just fit that, that coefficient will give you the central charge. So I just leave it as an exercise what the precise equation is. You should be able to figure it out from. So that's statement number 1. So you know what the central charge is. Good. Statement number 2. How do you figure out the scaling dimension? Let me again, for concreteness, just talk of Ising CFT, right? Because that's the easiest to think about. So in Ising CFT, if you forget the primary field, which is identity, then there are two non-trivial primary fields. One is sigma, one is epsilon, right? The important thing that we need to realize is sigma is odd under Z2 and epsilon is even under. Okay. Now you look at the spectrum. Find the lowest state above the ground state. Find the lowest excitation above the ground state, which is odd under Z2. Keep it in your bag, or rather in your computer disk. And find the lowest state, which is even under Z2, and store it somewhere. Okay. Then, again, from these two equations and stuff that I've written here, you should be able to show. So lightest means the closest excitation to the ground state. The C naught is the ground state. So from this plus higher order corrections in 1 by. So from this you can read off the scaling. Okay, you can just read it off. Now, what about the what is left? OP coefficients. So let's again just do the Ising problem. Okay, so how do you figure out the OP coefficients? Right. So for the OP coefficients, what you do is the following. Here you need to realize this fact that I told you before, that if you have a sigma field on the lattice, if you expand it, then there is a overlap of that lattice operator to the primary operator, but to all descendants also, which are Z2 odd. Similarly, if you measure the local energy on the lattice, so local energy is what? Sigma I Z, sigma I plus 1. You can just measure the local energy on the lattice, and you expand it in terms of primary operators, it'll have a non-zero overlap with the epsilon here, but it'll also have a non-zero overlap with all Z2 even descendants. Okay, good. So let's remember that fact. So let me just do it for sigma Z. So again, if you follow Cardy's prescription, there's a nice equation which you can derive. When I say Cardy's prescription, I just mean going from the infinite plane to the cylinder. Okay. So if you do those transformations carefully, you can derive the following. So here this phi p is like the primary operator. So this primary operator, which is a non-identity operator, hits the ground state and clearly creates some excitation, right? And this guy has the lowest excitation. So you take this overlap, and then this also has a universal form. Phi divided by L raised to the scaling function. In fact, there's an even nicer equation. So here I have a lowest excitation with some quantum number and I have the ground state. If here I also have another lowest excitation with some different quantum number, in fact, this 3-point operator gives you information about the OP coefficient. Okay, so I'll just write down the expression without deriving it. I'm sorry, because the derivation would take some time.
You might use probably the first step of that.
I am free to use any full board. It doesn't matter if it comes on a recording.
There is some sort of recording.
No, recording by recording.
This goes away.
So how much should I use?
You cannot.
I think you're already away.
So let me just go there.
That's it.
Yeah.
Yeah, I'm sorry that you're so I'm constrained on both sides.
Yeah, I know. Yeah, I actually completely overestimated my own pace. I should not have put this thing there.
Yeah,
But that's okay.
Then you'll have some more boards.
Yes, that's okay. So basically on the lattice, if you do this, and I'll explain the meaning of this equation. And for clarity, let me put this index here to remind you that this is a lattice operator. This is this OP coefficient plus some subleading corrections with sort of decay like this. Okay, so what is the sigma? This is the lowest excitation above the ground state, which is Z2 odd. What is this epsilon? This is the lowest excitation above the ground state, which is Z2 even. This is the ground state, and this you already know what it is, right? And this is the lattice operator. If you take this ratio and go to the large L limit, you can read off this particular structure. Similarly, you can read off other structure patterns. In more complicated CFTs, see, in Ising CFT is really nice. There's only one non-trivial Z2 odd primary, and there is only one non-trivial Z2 even primary. The moment you go to higher CFTs, like an Ising tri-critical point and so on, there are more than one primaries which have the same symmetry, right? There are more than one primaries which are Z2 even, there are more than one primaries which are Z2 odd. And then you have to do something much more sophisticated. But I won't go into that. But in principle, you can do all that.
Do the dimensions delta sigma and delta epsilon appear somewhere in this formula? Like,
No, but they get cancelled because I'm taking this ratio. Yeah, there's nothing else. You just pick out this OP structure factor as a leading term. Yeah, they get cancelled. All the ratios. Good. Okay. How much time did I already take? I didn't be doing well.
everything was like 45 minutes.
I took 45 minutes.
Yes.
Oh, that's okay. Then let me say some other things also. There have been a lot of discussion about this Ising tri-critical point and higher CFTs. So let me just say a couple of things in that regard here, because that'll be useful for certain things that I'll say later on. Okay. People like Connor already mentioned that you can get an Ising tri-critical CFT if you put vacancies in the Ising model. But let me just elaborate on that thing for one moment from a lattice point of view, and then maybe I'll just switch to slides for some time and then again come back to the board. Okay. So far, is it okay? I mean, I hope you see what is this state operator correspondence, why the CFT is only emergent. It never applies to the full problem, even if you tune the lattice problem to a critical coupling. Okay. But that's to be expected. Any questions on this?
But actually, let's say that there's some steps which show goes quick close to the ground state, and then there's some steps. So what is this gap?
No, it's not so easy. I mean, it's not that you can just separate this from that. You really need to see how the states approach the ground state as a function of system size. And only, yeah.
Actually, those states which are not approaching to the ground states.
Right.
We are doing an estimate that what gap is. I mean, does this get like errors or do this order one? Or what is it?
No, I think there will be some order one numbers. Right. Yeah. This 1 by L comes because these CFTs have Z equal to 1. Yeah. Okay. Okay, now let me erase this. I'm sorry, I have to erase things very frequently. And let me say a bit about this Ising tri-critical thing. Yeah. I'll just say it from a slightly different point of view. So It won't be a total repetition of what the others said. So there's this interesting model which Connor also referred to, but maybe didn't spell out the name. I know how to pronounce this Bloom. Probably this is Capel, probably. But if somebody knows the right pronunciation, he or she can correct. So you take a 2D Ising model again. So originally the Ising variables were I forgot what I used, sigma or SI, but let's use SI. Originally the Ising variables were SI equal to plus minus 1, right? Now let me just have SI equal to plus 1, minus 1 or 0. So plus 1, minus 1 are like spins and 0 is like a vacancy, right? So now you just write the same Ising Hamiltonian on a square lattice. This is the usual Ising coupling. And there's a new term, which is like a chemical potential for these vacancies. Why do I call it a chemical potential for these vacancies? Because see, for the spin, SI is only plus 1 or minus 1. So this D term is completely democratic in giving a shift to the plus 1, minus 1, but it gives a different shift to S equal to 0. Right? So it's like a chemical potential. Okay, good. And in particular, if you push D to minus infinity, you get back your Ising model because there are no vacancies here. But for more general things, so now there are two couplings in your game. In the original Ising model, you just had one dimensionless coupling, K, to vary. K has some absorbed temperature in it to make it dimensionless. You see, there's a temperature here. In the original Ising model, there was only K, but now there's K and D. So if you draw the phase diagram of this theory in 2D, like this, I think, then there's a very interesting phase. So again, there's a ferromagnet, there's a paramagnet. So these dotted lines refer to first order phase transitions. This thing is Ising scale. This phase transition is in the Ising universality. But you see that there's an interesting endpoint. This endpoint is your tricritical Ising scale. This is your tricritical Ising scale. Now, how do you sort of think about it? Okay, so that's why this is multi-critical. That's why you needed both K and D, and you needed to tune two things to reach this thing. If you just tune K, you won't reach this thing. It'll be an unstable fixed point. Okay? So now, okay, how do you understand why suddenly it became tricritical Ising scale?
So you have a line.
Yeah, which is all Ising,
Ising.
and it ends at tricritical
That is the
Ising,
point.
which is a different CFT, and then it becomes first one, where there is no CFT. Okay.
And the fact that you have a line of this Ising CFT and the point is just a point in this
Yeah.
space, it has to do with the fact
Yeah,
that
this is a multi-critical.
Multi-
Exactly. That's why you need two parameters to even reach there. So yeah, if you had a three-dimensional thing, this point might have been extended to a curve. You see? Okay. So now for this, you look at two correlation functions as a function of temperature. By the way, this model, unlike the Ising model, is no longer solvable. But let's say you go to a computer, you do some Monte Carlo simulations, or you can even do some very nice Coulomb gas things, or if you are Baxter, you can sometimes even magically write exact solutions. So, yeah. So you look at two correlation functions. This guy, right? And something else. This guy. So let's interpret these two correlations. This guy is a spin-spin correlation, right? Because as I said, S equal to plus minus 1 is like the spin in the original. This guy is like a vacancy correlation. Why? Because if any of these variables is plus 1 or minus 1, this guy just gives 0. Right? So it only picks out vacancy correlation. Right? So this is a correlator, this is a correlator. Now suppose you go out to your computer, tune at the critical point and see how these correlate. Okay? Then, so suppose you are raising your temperature. Let's say you are at some fixed D. Okay? Fixed D. And let's say you are raising your temperature. Okay? So this is your TC at that particular day. So you come here, you measure these two correlations. This correlation at large distances will go as 1 by 4, which is the statement that this is an Ising CFT. This correlation, this one, will be exponentially decay at that same point, Therefore, the vacancies can be integrated out because they are some heavy object and you just land up into an Ising CFT. Okay? Now you go here. You'll again see this behavior and this behavior. However, you'll notice that this correlation length has increased. Okay? Now you go here. You'll see that this correlation length, this is always a power, but this correlation length has increased even more. So the vacancies are becoming less massive, right? Now when you reach here, then these vacancy correlators also are powered. So now you have a new massless mode in your theory, and you anyway had another massless mode in your theory. So it's not inconceivable that these massless modes interact with each other and give you a new field theory. That's it. So that's how this field theory emerges from this very pedantic point of view.
What's the interpretation of this length scale psi? Because you're sitting at a critical point.
Yeah, that's correct. But at the critical point, not all variables are massless. This variable happens to be massive. Because it happens to be massive, you can integrate it out. Then it's like saying the field theory doesn't even care about the vacancies. So it's the Ising field theory or the Ising CFT. Okay.
Yeah, so if I were on the line and trying to move on the line,
On the
I should
line.
be able to
It's the same
put some marginal deformations on the line.
No, it's not a marginal deformation because this universality class is different from this.
Yeah, so but the line, I mean, is
No, it's not a marginal thing, right? Because see, on this line,
Yeah.
if you are a field theorist, you won't even care about the vacancies. You will only care about the vacancies here because a new massless mode has appeared.
And what I was trying to say is that if you, try and do something like that to flow between your rising and say,
Right.
there should be an endpoint somewhere with some sort of enhancement.
Yeah, there is an enhancement.
Yeah.
Well, there's an extra massless mode here, so there are extra primaries here.
Yeah, so I was just trying to say that is there any way to try to see that form in the sense that
This probably is, and maybe
Yeah.
Connor, do you know the answer? Maybe you did answer this question already in your talk. Or
Like master, and the master.
are you asking in a Landau-Ginsburg formalism, or are you asking?
If I just have an Ising CFT sheet with a marginal deformation to make sure that I flow, along that line.
I don't understand this thing about whether you can do it with a marginal deformation, because here it's 5-4, the field theory, and here it's just 5-6, 5-6.
That's at the end.
Yeah.
So I was just thinking if there's something emergent that something weird happens at the end of the flow, whereby you generate another.
Yeah, but I just don't know whether you can do it with a marginal direction. Probably not. Yeah.
We know that it's the marginal.
Yeah. Exactly.
It's not a real flow, it's what the same, it's all irrelevant deformations, there it's and all of this stuff.
Yeah. And at this fine-tuned point, the vacancies become massless.
Yeah, that's it.
So if you want in a field theory parlance, there's a fine-tuning problem. Yeah. No, but it is. Yeah. Okay, good. Since I am showing these slides, I should come to them at some point. So maybe I'll come to them now. Okay, good. So I'll come to them. So here, in Connor's preparatory lecture, we already saw that if the central charge is less than 1, there's a full classification of the CFTs, right? If the central charge is greater than 1, my understanding, my limited understanding of CFTs is that many things are ill understood. I'll talk about C equal to 1 CFTs. So C equal to 1 CFTs have exact marginal covariance, right? So what happens there is something called weak universality. So what does that mean? That means in your microscopic model. So usually the intuition is when you go to long distance and you flow in RG, most microscopic details become irrelevant, except global symmetries and some other emergent stuff. What happens in these models is there is some microscopic parameter in the theory, and you can actually tune that to tune the marginal operator and hence change the exponents and OB coefficients and stuff like that, right? So this is the special thing about C equal to 1 CFTs. C less than 1 CFTs don't allow for marginal deviations. I think that's what you said also, right? So, but C equal to 1 and higher can have marginal deviations. So that's why this term weak universal. Okay, that's the historical name given for this.
Can I just ask you
Yeah.
for clarification? So if I arrive at that tricritical point along the Ising line,
Yeah.
then I'll always find a sector of correlation functions which mimic Ising CFT.
No. At the tricritical point, there'll be a different.
Somewhere else.
Yeah,
Along
of course. You can look at this guy.
Yes, those are like Ising CFT.
Yeah.
Then there are hidden observables like other observables like those ones.
Yeah.
Which are not CFT.
Exactly. That's what I was trying to say. These are massive. So you can just integrate them now.
But so when you define the model, that's what, so this S varies from like,
+1, -1, 0.
0 also.
Yeah, I said that, but let me write it. That's important. That's vacancies. +1, -1 are the spins, and 0 is the vacancy. By the way, you can take the same route to get, let's say, Potts multi-critical points. So you do the same thing there. You don't do this. You have a Potts variable here with nearest neighbor interaction. That's like a Potts CFT. Now you put vacancies there. That's an extra variable which you just call 0. The other variables are 1, 2, 3, ... till Q. And that's it. This deformation allows you to approach a Potts tricritical.
So
Same
somehow,
thing.
I think, so you are somehow saying that the Ising operators are like contained in this Potts. I mean, you talk about your state picture.
Let's not talk of Potts. Let's talk of Ising. Yeah.
Okay, in this picture, so there are some states
Yes.
that correspond to the Ising model. Right?
Yes.
You haven't
Yes.
reached that critical point.
Yes.
But
It's
it's
critical point. Here.
the point on the
Yeah,
line.
this guy.
On the line, there are some states.
So let's
which will-
put some symbol here. Yeah.
Yeah.
This point.
Yeah.
Yeah.
So your state operator map, for which the states for which this is valid, that somehow increases at that point.
Of course, because there's
Yeah.
a new master node.
Yeah.
Yeah, that's correct.
Yeah.
That's correct.
So
And they hybridize in a non-trivial way. That's why the long distance power loss change. That's the point. Yes. That's the physical picture to keep in mind.
No, but the picture that you were giving in the previous slide,
Yeah.
there is a concentration and they go as 1/L.
Oh, that thing is all robust here, even here, because this is also CFT. But the universal data of this CFT will be different. Okay, let me see. I always keep forgetting these things, so I wrote it somewhere. What is the C for this? Of course, I should remember this, but no. This C is 4/. Oh no, 7/10. You're absolutely right. Yeah, that's the next one. Then 4/5 is the next one. Yeah, 7/. So, for example, the central charge of this guy is 7/10. Similarly, Ising CFTs just have 3 primaries, including the identity. This CFT has 1, 2, 3, 4, 5, 6 primaries. Okay, and yeah, they're all spin 0 objects.
So presumably in your picture of this, gap closing.
Yeah.
I mean, so there is one length scale, so this is the thing, so there's one length scale which is L, and there's another length scale which is
L is
psi,
the system size.
There is the system
Yeah,
scale,
yeah.
and there's another length scale which is psi.
Yeah.
So although even if you take L large,
Yeah.
if psi is finite,
Yeah.
then
There's a mass there.
So some states will not come in.
Of
That's
course. If you post grain enough, those states are just lost.
Yeah. So somehow at that point, Xi also closes. So more states come. I mean, Xi goes to zero.
No.
Xi goes to infinity. Sorry.
Yeah, it becomes infinitely massive in a RG sense.
Right.
Yeah. But you know what I mean.
Yeah.
Right? Yeah. Okay. Good. Good. So far, so good. So now let's come here. So I'll talk about some critical points which are C equal to 1 CFTs. So as you will see, these things, some of them were published long back, some things are much more recent, whatever I'm going to tell you. But there are interesting open questions in all the issues that I'll talk about. So I think thinking from a more refined CFT perspective might be useful for all of these problems. And I think I won't reach the third problem. So I was planning to discuss 3 problems, 2 concerning spin models and 1 concerning lattice gauge theory, but that's okay.
Yeah, 25 minutes.
In all,
Yeah, it's still at 25 minutes.
just 25 minutes. Okay, fine. Good. So, right. Let's see how we go. That's okay. There were enough discussions. So, okay. Oh, I cannot use this, right? Yeah. I should go this. No, there's no USB port here. So it's okay. It's okay. It's okay.
No, there is one.
Oh, is there? Yeah, okay. So these are sort of the references. I'll start with the 2D deformation of the Ising model. And you can see that these papers are ancient by modern standards.
Hopefully this should work.
What should we do? Yes, don't allow. Allow or don't allow? Allow. Okay, this allows. This allows. What is this? Then this. Okay. Wow. There's a MacBook, right? So it's extremely advanced.
Give it that more.
It's okay, don't worry. Sorry, it's fine. I'll just use this stick.
It's just
I'll use this
sad thing about just switching it on and off.
Oh, now and then working.
Okay, good.
Wonderful, thank you. You have already passed the experimental methods course.
Right, so.
Okay, so these 2 works are sort of oldish, but I'll first describe this because there's an easier introduction to what I'm going to say. And in fact, this will also bring into picture something which I didn't discuss, which I erased, which was what was called walking RG flows. Okay, so I'll come to that if I have time. Otherwise, maybe Antonio will discuss it. Anyway, I'll come. And then these works, these 2 works are more recent, and they concern a particular quantum spin chain. And again, we see C equal to 1 phase transitions there. And this is the work on the lattice gauge theory, where we see a confinement deconfinement transition as we raise temperature. And again, there's a C equal to 1 conformal theory. But here we understand the least. For example, here we don't know how to construct the marginal operator. But probably that's inevitable because this is the most complicated. Anyway, but let's go on. So this I already said, we don't need to look at this. Basically, the important thing is that under RG, when things flow to a fixed point, of course, the irrelevant couplings go to 0. And there are only a few relevant couplings for lattice models where you might do experiments, right? Which basically means that the fact that so many relevant couplings goes to 0, it basically means that most microscopic details are utterly unimportant, and that's why universality can emerge, right? And just to give you a cool example of that, this we know, this is just this Ising critical point, let's say in 3 dimensions, right? So of course, if you turn on a magnetic field here, it can also have a first order transition, but there's this Ising CFT also in even higher dimensions, Ising fixed point. Now, if you look at a problem of like water or some other fluid, that also has this critical endpoint here. Now, it's a miraculous statement of universality that the field theory of this guy and the field theory of this guy are identical, even though the systems are completely different. And this is pretty non-obvious because here it's obvious what is Z2 odd and what is Z2 even by construction of the theory. But here what is Z2 odd and what is Z2 even is actually emergent near the critical point. Because in a liquid, there's nothing obviously Z2 odd and Z2 even. So this is an example of emergent symmetry. Okay, good. Okay. And anyway, this I already said. I'm just considering some sufficiently short-range interactions. And in 2D, basically I'm considering problems where there's an emergent translation and rotational symmetry at criticality. And in 1D, I'm considering problems where the low energy dispersion is linear right? And such thermal or quantum phase transitions are described by 2D CFTs. Okay. Oh, sorry, it's a bit slow. This already I told you about, right? This is the Drosophila of lattice critical theories because this is completely solvable. And for those who don't know what is a Drosophila, it's something which is used in biology labs. Okay. Yeah. Okay, you found it funny. Okay, good. Somebody found it funny. Okay. Right. That's because we were in the same graduate school, so that's why he found it funny. Okay. So, right. Okay. So you already had enough of Blackboard. Okay. Now here is the model, which is already a non-trivial generalization of Ising. So just consider a regular Ising model, no vacancies now, ±1 on each side of the square lattice. But now, instead of just nearest neighbor terms, you even have next nearest neighbor terms, which are indicated by these red crosses, right? And this nearest neighbor term is ferromagnetic, and this next nearest neighbor term is antiferromagnetic. Okay, so this likes to anti-align spins, whereas this likes to align spins. Okay. This model, and I have written that here, so there's a minus sign here which you should be careful of. So this model, and this is G by the way, G is J2 by J1. So there's a coupling G in the theory and there's a coupling T. Let's measure T in the scales of J1. So this model cannot be solved. Okay, there's no exact solution. And now the question is, so this is a very simple generalization of the Ising model, but you will be somewhat perplexed to know that till date, there's a huge controversy regarding its phase transition. It's such a seemingly simple model, but there's some controversy regarding its phase transition. So let's.
Can there be a continuum description in terms of the field theory?
Yeah, of course, there should be. Yeah, because it's all a local thing, so there should be a field theory description. Everything. So let's go on. So let's first look at some simple limits here. So suppose this G, which is J2 by J1, is less than half. Then if you just look at the ground state of the problem, you can show that all the spins are either all up or all down. That you can show. Okay, if it's not immediately obvious, if you think about it a bit, you'll be able to show. When this G crosses half, and again, you're just concerned about the ground state, that's just some optimization problem, right? Then you will see that the ground state nature changes in time. So then there's something called a striped order which emerges. So if you look at these spins, let's say these are all up, then this line is all down. Then this line is all up, this line is all down, and so on. So that's why I'm calling it stripe. So it's a stripe of up, stripe of down, stripe of up, stripe of. And if you stare at this picture, you will be able to see that this ground state is fourfold each. Right? Because there are four ways of arranging the stripe, right? Up, down, up, down, down, up, down, up, and the same thing horizontal. So 4 ways. So, but here there are only 2 ways. Okay. So here, if you heat up this theory, this line is all in the Ising universality. Now, what happens here? Here, this is going from one type of solid order to another type of solid order. So at t equal to 0, this is a first order phase transition. Right? Because it's abruptly going from this guy to this guy. So it's a first order phase transition, right? So this guy is first order, this guy is all Ising. Now let's look at G tending to infinity. When G tends to infinity, you can forget about the nearest neighbor interactions, right? Because J2 is much larger than J2. Now you need to just turn your head, like literally, and try not to fall out of your seats. Then you'll just see that there are 2 interpenetrating square lattices. You can see that there's this one guy here, and there's another guy here. So at G tending to infinity, there are 2 decoupled Ising models. Okay, so again, you will have a Ising universality, but there are 2 of them. So it's C equal to half plus half, which is C equal to 1. Okay, good. So this is first order. That is Ising universality. The question is, what happens in between? That I cannot guess by pure thought, unfortunately. Okay, good. Now, what happens was controversial for a long time. Then we wrote some papers, and they were reasonably influential in clearing the uh, issues. But I still believe there are lots of things which needs to be. So, roughly, what's happening is that there is Ising universality there, and then the thing stays continuous, but its universality class keeps changing. And it flows all the way from Ising universality to a Q equal to 4 Potts critical.
When you say Ising, I mean Ising squared.
Exactly. Thank you for that. I should actually, yeah, it's Ising squared. So it flows from Ising squared to Q equal to 4 Potts universality.
Sorry, this one is also Ising square.
Which one? That one, no, that's Ising. That's Ising because there are only 2 degenerate states. Yeah, this is conventional Ising. That is Ising square, and it flows to Q equal to 4. See, here the exponents stay the same. Here they keep changing, right? And here there is actually a marginal operator, which is actually pushing you from there to here. Okay, and then below this, and this is actually very non-trivial. Below this, there's an entire line of extremely weakly first-order phase transitions. And therefore, my statement about walking RG flows. And if I have the time, my second statement about complex CFTs. If I have the time. How much time do I have? Right? 15. It's 15.
Can I just make a comment?
Yes.
CFT person would guess that that phase transition needs to be equals to 1 at all.
Yes, sorry, say that again, please.
That phase transition, on at least sufficiently on the right.
Yeah.
A CFT person would guess it must be C equals 1 compatible.
Correct. It is.
Yeah. By the symmetry.
Which is?
Just by the symmetry breaking pattern of the.
Absolutely. Yeah. I mean, many of the things here we could sort of the possibilities we could guess from pure thought. And I'll tell you how you can guess it. But then because it's a non-integrable theory, you ultimately have to do numerics to make everything consistent and see what's happening. Right. But many of the things can be argued from pure thought. That's correct.
So but what happens to marginal deformation after you hit when you hit this point? Is that a wall? I mean,
I'll come to that later if I reach the runaway RG thing.
Going back to Shastri Sutherland like model which is interpolates with the square lattice and this
I think, sorry, you're saying this is like the Shastri Sutherland?
No, if you remove one set of the bonds, then you can make like a Shastri.
Yeah, then you can make it. Yeah, that's correct. But here these bonds are included because I wanted a theory which has the same symmetry globally, like the square lattice symmetry and all. Yeah. So
yeah, I was thinking like you take the Shastri Sutherland and let's say weaken the bonds.
Correct.
You like go to this.
But that'll go to a triangular thing. Sorry, if you remove one set of these red lines.
Yeah, if you remove the red lines, then you just go to this one.
Yeah.
And then if let's say I add the other line,
yeah,
then I go to this model. This checkerboard.
Yeah, but yeah, I think nobody has looked at that. Yeah. So when transitions are very weakly first order, that's also very non-trivial. Just to give you one example, the Q equal to 5 Pot states model on the square lattice, that has an incredibly large length scale. So when something has an incredibly large length scale, but that length scale is finite, there should be a good explanation. Right? So, but we don't have a good explanation. So that's already an open problem, which I think is interesting. Okay, good. Also, locating this thing is pretty non-trivial. So now, actually, I'll just draw something on the board here. And there's this beautiful paper by Worley brothers and a third person who's equally non-trivial, whose name I'm forgetting. But yeah, that's good. Thank you. Yeah. Which discusses these C equal to 1 CFTs very nicely. So basically, there's some marginal deformation. This is related to what Antonio also said. This goes from Ising square all the way to equal 4 Potts, and on this side to the famous Kostelis-Thouless phase. This is the scenario from pure thought. Now the question is, where are you here? This is a microscopic theory. That you cannot do from pure thought. If transitions are continuous, then from pure thought, I know that the transitions are somewhere. And I already know that when G tends to infinity, this is correct. But for finite G, I need to do a calculation. I don't know whether it's this or that or whether it's a first order function. Any microscopic theory can always go to a first order. That's, uh, these CFTs are connected together by a marginal deformation. It's not to say that these are the only known C equal to 1 CFTs. There are other C equal to 1 CFTs, but they are slightly separated. And they all have central charge 1. Sorry, I should have written. In fact, if you have central charge less than 1, you don't have marginal deformations because you only have a discrete set of CFTs. Oh, this is a bit slow for some reason. Okay, let's do that. So now, if you are slightly above G equal to 0.5, then you already notice these hints of the first order phase transition. So how do you notice that? I already told you there is a four-fold symmetry breaking. So you can define a two-component order parameter like this. Yeah, okay, this is on the square lattice, and there's an mx you can define, and there's an my. And basically, if you just calculate this order parameter for these 4 states, you will just get these 4 points on the 2D plane. Okay. Whereas if it's a paramagnet, you'll get the origin. Okay. Now, if you look at this probability distribution of the order parameter, okay, and let's say some G equal to 0.55, right? And you just vary your temperature. So you see what's happening here. There's some color plot. Because somehow condensed matter physics love color plots. So there's a color plot, and basically the bright color means high, and my God, whatever this color is, orange or red, just means low. Okay. So you see when the temperature is whatever, this 0.771, and these things are generated using Monte Carlo data, you see that the order parameter is high here. That basically means it's in the ordered phase, right? Whereas when the temperature is 0.773, the order parameter is clearly very high here. But in between, there seems to be a coexistence of phases, which is a classic signature of first order phase transition, right? But when you have first order phase transitions, there are certain scalings which are known to be asymptotically valid. Okay. So for example, if you look at the specific heat divergence at a finite system size, the specific heat should diverge as L to the D, where D is the dimension of it. If you have a continuous phase transition, there's a non-trivial number here, which is a critical exponent. In fact, it's alpha by mu. But for a first order transition, this is D. And similarly, all scaling exponents in first order are either D or 1 by D. Okay, and one can show that. So if it's really a first order transition, you should see that. So the question is whether we see that. So for example, you track the specific heat height, and this line is basically a line at which is scaling as L squared, just as a guide to that. So you see, and this is system size, so it's already 100 cross 100. Right? So you see, if you look at it with a very loving eye, then at least at G equal to 0.51, it's converging to L squared. But at G equal to 0.55, it's nowhere close to this slope, which is already a signature that there is a large length scale which is clearly greater than 100, beyond which maybe it will go to L squared. Right? So this is already weakly first order. That's the meaning of weakly first order. Okay, good. And of course, if you go to some other G, then this length scale is even more. Like as you approach that equal to 4 pots. Okay. Well, now, okay, maybe I should say this because we are talking so much of marginal operators. So suppose, so you ask yourself, how can you generate a marginal operator in an Ising CFT? Okay, so in an Ising CFT, if you remember the OP constants, then if you couple an epsilon to an epsilon, you just get identity. Okay, right. But now imagine you have 2 decoupled Ising models. Then you can imagine coupling an epsilon 1 to an epsilon 2. because there's one epsilon 1 for this theory, there's one epsilon 2 for that theory. So if you look at the correlation function of epsilon 1, epsilon 2, which is highlighted in blue, it's actually an exact marginal operator at the Ising square CF. Because you know the scaling dimensions of this operator there. You can just calculate the correlation function and you will see that it's exactly marginal. So at least in a perturbative RG sense, you have identified a marginal operator. Okay. Now you can be bolder. You can say, okay, let me take this intuition to a lattice. So let's take this intuition to a lattice and write this model. So this model is nothing but there's one square lattice and there's another square lattice. And there is a sigma I here, which is your usualizing variable, and there's a tau I here, which is another usualizing. So this thing, if you ignore this k part, is two decoupled Ising models. So that's Ising squared. Now you couple them. So how do you couple them? What is the marginal operator I wrote? Epsilon 1 times epsilon 2. What is epsilon 1's lattice realization? It's just sigma I, sigma j. And what is the thing here? Tau I, tau j. We just couple the four of them. That's this term. Right? Now this term is really a marginal operator on the lattice, and there is beautiful work by several people, and I'm misciting many of them. There's a very famous model in StatMech, it's called the Ashkin-Teller. Okay? And in the Ashkin-Teller model, if you vary k, okay, you can reach all the way from the KT transition to the decoupled Ising to the pods. Decoupled is easy, it's k equal to 0. Pods is something like k equal to 1. Right? So this red line is this thing. This is decoupled Ising, this is pods, KT is somewhere over there. Okay, so this is a beautiful illustration of a lattice problem where you can show all this.
So, but the other thing that you were showing, the Ising square thing, the two J's were having a different sign, J and J.
No, but this is a different theory. This is a different lattice theory.
But when you say Ising square here,
yeah,
and the Ising square there,
that Ising square is the same. But so when k is equal to 0 there and when g is tending to infinity there, they are microscopically identical. But for any other set of couplings, they are microscopically distinct here. But I can make universal statements. So,
Is this model exactly solvable or also not?
no, this model is not exactly solvable, but many properties of the critical point are exactly solvable. A using duality. So, for example, this red line is self-dual, and B using Coulomb gas matrix. But the model is not exact, apart from the Ising. Good. So one thing to realize is on this line, even though the exponents are changing, for example, the correlation length exponent, but if you look at the ratios of certain exponent, like beta by mu or gamma by mu, they are constant. So this guy is 7 by 4, no matter where you are on this line. This guy is 1 by 8, no matter where you are on this line. Okay? So this was highlighted, and eta is always 1 because you're deforming by marginal operator. Okay? Good. Let me not go into that. So, yeah. So let me just tell you some signatures of this fact that this is a weak first order transition. So there are certain objects that you can define. There are certain objects that you can define which help you track the universality of something on finite lattices. So one object is a Binder cumulant. So what you do is define some dimensionless ratio of order parameters. So this m is the order parameter, and it's a vector order parameter, right? Because it's a 2D order parameter. You define expectation of m4 divided by m squared, and you do some normalizations here. And once you do all that, this Binder cumulant, which is conventionally called U2 in the literature, is a very interesting object. It's actually a step function in the thermodynamics. So this U2 is ordered, and it's 1 on the ordered side, and it's 0 on the disordered side. And it's got to do with how I've chosen these ends and all, which I don't have the time to explain. And very non-trivially, it's a universal number at the critical. So it's some U2 star at the critical. Why? Because it's a dimension 0 object. So you would obviously think it's some non-trivial number at the fixed point. So it's some universal number which is characteristic of the fixed point. Okay. Good. And you can even use the behavior of these on finite lattices to track the critical point of it. So for example, you see that it's approaching a step function as you keep increasing the system size. But if you look at its crossing for different system sizes, you can track the transition. Right. Now there is a very interesting difference between the build accumulant for continuous phase transitions and first order phase. For continuous phase transitions, this build accumulant for any finite size is a monotonic function of temperature. Please follow my hand. There's a monotonic function of at finite temperature. For first order transitions, it's actually a very peculiar non-monotonic function at finite temperature. Again, you see how it's going? It's a non-monotonic function. And as we increase system size, this dip keeps on increasing in the negative direction. So for a strictly first order transition, this dip will go to minus infinity as n to the t. That's a diagnostics of a first order transition. So if you just stare at this build accumulant, you know whether a transition is first order or continuous. Now comes the thing which confused many people historically when they were looking at this. So the thing is, I did not write that here, but let me write it. This G star, above which the transition is continuous, is something like 0.67, which we numerically estimate. Even if you go above that, let's say 0.70, 0.75, you still see negative dips. You still see negative dips in the building. And people thought that's because it's a first order transition. Okay? But actually, that's not right, because I know for a theoretical fact that in the Ashkin-Teller model, the Q equal to 4 pos point is a continuous phase transition, and its neighborhood is also a continuous phase transition. So there's all a continuous phase transition. If I calculate things like this for the Q equal to 4 pos model or its neighborhood, I'm jumping some things, but that's okay. So this K is supposed to remind you of that. This K equal to 1 is the POTS thing in the Ashkin-Teller model. This K equal to 0.95 is slightly here. If you calculate that, you again see negative building. Right? But we know asymptotically these are continuous phase transitions. The reason this happens here is not completely understood, but roughly speaking, the thing that tells you that this is not a first order phase transition is if you look at how these dips increase as you increase system size, is nowhere close to L to the D. It's nowhere close to L squared. It's actually something like log of L. And as I'll soon say, logs are pretty important for Q equal to 4 pods. Okay, so basically this Q equal to 4 pods and also this KT, these are examples of what are known as multi-critical CFTs, where all kinds of multiplicative log corrections appear to the normal scaling. And if you're not careful of that, you're just screwed. Okay? So if you perturb around here, or if you perturb around here, you have to be really careful in what you're doing. Okay? So people have been misinterpreting lots of things and we're overestimating where this thing is, and then we corrected them and whatever. My time is up.
What's the statement? If you take care of the log things, it's actually, you understand that irrespective of the dip, it's
Exactly. Exactly. But that log is always present. It's not like it's a, how should I put it? It's a multiplicative log. Okay, I'll come to that. Maybe you'll give me 5 more minutes or something. Or what do you want?
Yeah, sure. But people, I'm very hungry, so.
Oh, who's hungry? You are hungry. I don't have my cell phone with me. I don't know what's the time.
It's 108.
Oh, sorry. Okay, so maybe I'll just say, how should I say it?
Yeah, I think 5 minutes is fine.
Yeah, sure.
Yeah. So, okay, maybe, yeah. But what was your question?
No, I was feeling up. So I wanted to understand the statement that even if there was a dip, as you showed in the right hand,
But it doesn't necessitate a first order transition, especially if you're in the neighborhood of multi-critical CFTs, which we realized. Yeah. If you're here, then this does not happen. But if you're here or here, then you have to be really careful.
What non-dimensionalizes the L inside the log?
Sorry, what?
I mean, what log L is like.
There's some lattice scale or whatever, L by A or something.
And the correlation, the power law behavior of the correlation function is gone.
No, it's not gone. So maybe I'll just show that and then maybe I'll stop. Okay, yeah. It's not at all gone. It's an extremely important. So, yeah. So I'll jump to something else, which is a quantum problem, and I won't describe that, but I'll just show you that log correction. So, yeah. Okay, but I'll just describe this model. Anyway, we have 5 minutes. So, so don't take the Ising model. Just take this model on a 1D line. On a 1D line. So you see there are 3 spin interactions here. This is a very beautiful model. This is non-integrable, this model. You cannot solve it using Jordan-Wigner fermions or any other way. Okay, but this model also has a self-duality just like the Ising model. And the critical point is still at h equal to 1 and h equal to minus. Okay? And here we realized in some other work that this critical point is actually a q equal to 4 Potts critical. Okay? Even though there are no 2 copies of the Ising model. Right? In the Ashkin-Teller, there were 2 copies of the Ising model. There's a single Ising theory. Right? But there's a q equal to 4 Potts. But let me come to Parijat and Gopin Moyes and others' questions about this log. And I have to find it myself. Yeah, here it is. Yeah. Right. So you see, if you had conventional scaling at the Potts critical point, then delta is what? The smallest gap of your spectrum. So delta times L is some universal function near the critical point. It should be a scaling function which is just a function of h minus hc times L to the 3 by 2. This 3 by 2 comes from one of the exponents of the Potts theory. You would close your bracket here if it's a non-multi-critical CFT. But if it's a multi-critical CFT, there's an extremely non-trivial correction, which is log L to the minus 3 by 2. And you know how slowly logs decay, right? So here I just show some DMRG data. If you do DMRG till 390 spins on a chain, which is a pretty large lattice size for all practical purposes, you will see that the exponent mu is 0.72. It's not 2 by 3. Okay, it's 0.7. So you don't get the right answer, even if you go to very large systems. But if you incorporate this thing, then you actually see that your exponent is what is the Potts exponent. So it's extremely crucial to incorporate this. And you see, you can never ignore this thing. I hope you see what I'm trying to say, because it's a multiplicative thing, and no matter how big your L is, it's sitting on a multiplicator. How do you do this? Right, so, yeah. Okay. In fact, if you don't incorporate this log function, you will see something called a floating exponent. Your exponent will just keep floating with increasing system size, it will not approach the correct one. So this is really important. Anyway, we realized this here and in the other context, and yeah, the mystery was kind of solved. And let me just make one comment and then I'll stop. I'm really sorry for taking so much time. So in the Ashkin-Teller models, there was a marginal operator I could write, which took me all the way from q equal to 4 to decoupled Ising squared. Now let me ask the reverse question here. Here I know that in this very interesting model, h equal to 1 is a realization of is a lattice critical realization of the q equal to 4 Potts point. Question is, what are the marginal operators I should turn on here so that I go to Ising squared? And this is a really non-trivial question. Of course, I cannot explain to you why it's non-trivial because I haven't explained anything to you. But I'll be happy to talk about it later. Okay, so thank you for your indulgence, and yeah, thanks. Yeah.
So maybe one quick question and then we start.
You asked a lot of questions.
Yeah, there are a lot of questions. Okay, so there are no questions. We can just ask questions informally and can this be.